All right. Ah, hello, everyone. It's me. Ooh, too loud. Don't do that. All right. So I'm gonna exist here today because I have the sniffles slash who knows what. But I got it Friday, but I'm still sniffling stuff. So I'm just gonna exist in exile behind this desk, and then you'll have to rely on Peter and Sophia, which is probably better anyway. Yeah, and I'll sound slightly nasally, so that's exciting, right? All right. Peter and or Sophia has okay. Sophia has the joke.
You can't plant flowers if you haven't bought any.
Because botany is like the study of plants. Because it's related. Anywho. Okay. We're doing fluids. So that's exciting. For good or for bad, I also started making your all's second exam. As I mentioned, I think it's going to be easier than the first one because the content I think is a little bit easier, and then just you're better prepared and all that good stuff. My goal / my hope is to make some kind of practice exam for you all, but we'll see what that looks like. What I don't want to have to do is make a whole nother exam because that just takes forever. But that's kind of what I'm going to have to do. So whatever. I'm going to sample from the quiz questions and do things. So we'll see what I can do in a reasonable time frame. But if I make one of those, my goal is to make one before spring break so that it's actually useful, as opposed to if I give you after spring break, it's kind of, I don't know, not as much time. Otherwise, like I've told you all, most of the test is momentum and energy. That's really what you should be focused on. But then, so the free response will be, no matter which free response you pick, one part of it will be momentum, one part of it will be energy. Either part A will be energy and part B will be momentum, or part A will be momentum and part B will be energy. And then the test itself, out of the 24 questions, I think at least 6 will be fluids. At most 8 will be fluids. But then the other 2/3 is energy and momentum. So, so anyway, energy and momentum is the main thing. You definitely do want to practice fluids though, because so here's the learning objectives. It's a lot. There's a lot of different things in fluids. There's a lot of things I have to cover in here. Each one of them is fairly simple, but it's a long list. So I'm not going to be able to ask a question from every single topic. There's how many bullet points here? 1, 2, 3, 4, 5, 6, 7. There's going to be at least 8 things or something I teach you in this slideshow. If I only ask 6 questions, obviously I'm not going to get to all 8 things. So this is something you want to do. You don't know which of the things I'm going to pick. Yeah, we'll go through this though. It's really, really interesting. It's all, again, every one of the principles is really simple. But fluids is something you're going to want to practice. None of the problems, in my opinion, take too long. They're all really basic equations, all that kind of good stuff. So the first thing I taught you all, you all know this, is density. But the thing I kind of conveyed to you all that you might not have realized is the units are going to be kind of annoying with fluids. So you might have grams per centimeter cubed. And, I need to mark this as not true, because this is not true. 1 gram per centimeter cubed does not equal 1 kilogram. 1 gram per centimeter cubed equals 1,000 kilograms per meter cubed. And we talked about that, whatever. That's the density of water. And that's listed right here, 1 times 10 to the 3, yay. 1 liter is 0.001 meter cubed, yay. All right, this stuff's going to show up. This is a really common theme in fluids. When we get to pressure, there's also going to be 2 different units for it, and it just is what it is. Why is there different things? Because different disciplines are finicky about stuff. In the medical field, you all are going to use, well, we'll get to pressure and I'll tell you what you all are going to use in the medical field, but then it's different than what we use in physics, so whatever. All right. So we did a problem, density or mass, whatever. Okay, so here's the first problem. And there's going to be a lot of problems we're going to solve through in this PowerPoint because, again, there's so many different things, so I got to show you how to do them and all that good stuff. A 2.5 kilogram still gas can hold 20 liters of gas when full. What's the average density of the full gas can, taking into account the steel as well as the gas, taking into account everything? The density of gas is 0.68 times 10 to the 3, and the density of steel is 7.8 times 10 to the 3. And then, there's the answer. Why would we want the average density? And I gave you all the example, I think, last class of this. So the human body is made up of a bunch of different stuff. Fleshy bits and bones and brains and livers and muscles, and all of them have different densities. But if you calculate the density of the human body by like sticking yourself in water or something, it's going to give you the average density of everything. And then you can work backwards to find the density of like how much fat's in a body. That's actually one way that they do like fat percentage is they stick someone in water, they measure their density, and then from that they can back calculate the amount of fat in someone's body given their volume and things like that. But anyway. Yeah, think about how you all would solve this. See if you can come up with a process for that for this problem, that's awesome. Here's a picture. There's a gas tank filled with gas. It's a milliliter is the same thing as a centimeter cubed. And if y'all notice in this problem, it's got all the funky units. Okay, no, it doesn't. It just has liters.
Your average is bigger than both of the numbers that went in.
Oh, that's nuts. That's wrong. No. No, it's smaller. Oh, you're right. No, it's E2. It's in between the two, because it's E2. This one's E3. This one's 7.8 E3.
Oh, I didn't even see those.
Yeah. Oh. Yeah.
Maybe make them both also in E something notation.
Oh, sure. Yeah. Times 10 to the 3, E2. Yeah. The problem I had it written is times 10. I am totally going to mute myself every time I do that. Oh, it's big. No, it's bigger than the gas. It's in between the two.
Yeah.
That's all right.
This is why notation should be consistent.
Yeah, but this problem, they use the scientific. I tend to use scientific in the problems because that's the most common that they'll see. And then I use the E notation in the answer because that's just what I use. So yes, I am a little chaotic here.
We have like math, so we have meters to meters cubed. That seems too easy.
Yeah, this problem does have a couple steps. Yeah. A couple. You got to do 3 calculations total. You're going to plug stuff in your calculator 3 times.
I know what one is.
That's good. Then you can maybe work from there. All right, so
Maybe we find a mass of the gap.
remember the strat first is what are we even solving for? Like that's always, where's our eyes fixed upon? We're solving for density of like the whole thing. So they call it average density, which is, density of everything. And then we can go back and we write down our givens. Ooh, it's so echoey. All right, so You got the mass of the steel. We'll just use MS for that. 2.5 kg. We got the volume of the gas, which is 20 liters. Because our densities are given as meters cubed, we're going to want to convert liters to meters cubed. Basically, pick a unit and stick with it. Pick what you're going to work with and stick with it. If you want to stick in liters, awesome. Then you need to convert everything to liters instead of meters cubed. If you want to work with meters cubed, great. Then you need to convert all your liters to meters cubed. So yeah, that's a good check. Go ahead and convert liters cubed. And this is a unit conversion I don't currently have on the test, but I'll be happy to give it to you all on the test. I don't need you all to have this memorized, liters to meters cubed. Yeah. You gain very little by having it memorized, so I don't really care. So 1 liter is 0.001 meters cubed. So you just... There's just 20 of those. If 1 liter is 0.001, then 20 liters is 20 times that. Meters cubed. All right, then we also have the density of gas, which is 0.68 E3 kilogram per meter cubed. And we have the density of steel, which is 7.8 times 10 to the 3 kilogram per meter cubed. I haven't taught you all this, but like everyone, I think most people know this. One of these will float, one of these will sink. Which one does what? The gas will float and the steel will sink. How'd you know that? So you all might have seen that gas floats on water. If the density is less than the density of water, it floats. That's a really easy rule. I'm not going to test you all on that, but that's just like a super handy thing to know. The density of water is 1 times 10 to the 3. Gas is less than that, so it floats. Steel is more than that, so it sinks. That's literally the rule for why things sink or float, is just you compare the density to water. If it's bigger than that value, it sinks. If it's smaller than that value, it floats. All right. Cool. All right, so I'm going to start to set up step 3. We're going to calculate density. What's literally the only equation you all have for density? Density equals mass over volume. So how are we going to solve this problem? Find the total mass, find the total volume, and divide them. That's the thought process. Density is mass over volume. So find the total mass of everything. Find the total volume of everything. And then do. Yep. Yeah, you can leave everything in kilograms. As long as everything's consistent, you're good.
That explains all my numbers.
Density and convert the density of steel and gas into something.
And if you haven't realized this yet, you need to find the mass of the gas. You need to find the volume of the steel to actually solve this problem.
Yeah, okay.
And all these numbers should make sense. You know, if you have a gas tank filled with gas, the gas is going to have a decent mass to it. Like, there's a lot of gas in there. The steel's not going to have much volume because its volume is how much space it takes up. The literal steel of a gas can does not take up that much space. Yes, the entire object does, but it's filled with air. Like, we don't count that. Yeah.
In the yellow you just wrote.
Why?
Of the steel.
Yeah.
Why don't we times it by 1/2.5? Then when the units cancel out?
Yeah, so if you solve... So the question was basically rearranging this equation.
Yeah.
If you're solving for volume, you're going to kick volume to the other side. So you're going to have volume times density equals mass. And then if you want to solve for volume, you're then going to kick the density over. Yeah, this is one of those, like,
Okay.
this math process is like one of the most common math mistakes I generally see. Anytime you have this kind of setup where you have something equals something divided by this, super, super common. Yeah. So I appreciate you asking it so I could show it to you.
Thank you.
Yeah.
So then the math. Yeah, that makes sense. I did that times 10 over.
All right. So yeah, on the bottom, I'm just plugging in the numbers. So 2.5 plus 13.6, that's our total mass. And then we're going to divide that by our total volume. And yeah, we get the answer. So that's exciting. 792.28 kilograms per meter cubed. So will this float or sink? Is it less than 1,000 or bigger than 1,000? Less. It's gonna float. Yay.
So I got 793.1 because I didn't do 0.00031. I just did 0.003.
Oh, okay. That's
I
fine.
just did the 2 1 at the
Yeah.
end. Is that okay?
1 to 2%.
Okay.
1 to 2%. Yep. Always. It's a great question. Someone was asking. Their answer was slightly different because they did some rounding. As long as you're within 1 to 2%. That's always the rule of thumb. So yeah, density. Yay. Lots of fun. Okay. So density is going to get used a lot. Yeah, it's going to show up a lot. We're not actually, the only reason we're going to use mass in a problem is to find density. Like, that's going to be the name of the game when it comes to fluids, is you really, really care about how dense a fluid is. It affects, like, so much about the fluids. Yeah.
On the yellow part, you have S.
Yeah.
Say N 50 or is that?
Yeah, the mass of the gas divided by the density of the gas. Yeah. Yeah, spot on. And then Y volume is mass over density I did up top. If you rearrange the density equation, you multiply the volume to this side. So I multiplied the volume times density. And then to get volume by itself, you then divide by density. So,
Wait, but if you said that the volume is the density of the gas, then why do you have the density of the steel?
oh, because I'm silly. Thank you. Great catch. I put the right numbers in, but I totally labeled it wrong. You're not going to follow the volume of the steel by using the gas. Awesome. Yeah, thank you.
So is this something they do for like a cruise ship? Do they like kind of calculate the average density of the?
That's a good question. Yeah. No, I don't know for sure if they actually. They're going to calculate how much of the cruise ship will be above water for sure. Yeah. And actually, I'm going to teach you all something that's really interesting is the amount that's going to be above water. I'll teach you all this in a few slides. If you all take this and you divide it by the density of water, that gives you the percentage that's going to be underwater. So if you take the density of an object and you divide it by the density of water, it's going to tell you how much is going to be below the water. So in this case, how much is going to be below the water? 79%. It's going to float, but when things float, they don't like just sit on the surface of water. Like, that'd be wild. We're going to learn later on, so that's a really good question. This thing's going to sit, it's going to float, but 79% of it will be below the water. And it's literally just take the two densities and divide them. So for cruise ships and things like that, I imagine they do something related to that where they figure out how much of it's going to be below water and then how many crew members can you add. I mean, they're not going to change too much, but cargo and things like that. Yeah. I don't know what they do exactly for the calculation.
Yeah, because imagine you only put so much cargo until like it's too below.
Yeah, they might do that. Like, they might just do a simple calculation of like, oh, you got a steel frame and there's this much air inside it and things like that. They might do that. I actually don't know how in-depth. They probably get very in-depth. You don't want to build something the size of a skyscraper and then have it sink. So the ballast tanks are actually to shift the center of mass kind of lower. So the ballast is extra weight they add so it doesn't tilt over.
But it's also like you're filling it with water, so then it's like.
Yeah, that's to actually make it stay lower. Because if you add more mass to it, it's going to actually make it go down. So yeah, ships actually want to add more mass. Because if you all have ever played with like a bath toy, like a rubber duck, and you like put it in the water and it like falls on its side, and then it floats that way, you don't want a cruise ship to fall on its side. It's still floating on its side. So they'll actually shift the center mass below the water because if the center mass is above the water, it's going to want to fall over, which is kind of interesting as well. Anyway, all right. So density, super important when it comes to fluids. What else is super important? Pressure. Pressure, really simple calculation. Force divided by area. There is so many units for pressure. My goodness. Now, in our class, we're really only going to use a couple. So newtons per meter squared, that's like our metric units. We call those a Pascal. Like 1 Pascal is 1 newtons per meter squared. They're the exact same thing. So that's nice. So the base, the metric units are this. In the medical field, you all very likely are going to use millimeters of mercury. So that's whenever you take like a blood pressure measurement and it like shows you a number, it's based upon how much mercury, oh goodness, I don't even know exactly what it does, like goes up in this like tube or something. I haven't actually looked at the mechanism of how the...
It's like a tub of water and you have like a inverted tube.
Oh, okay.
Water and you have like the air pressure, it pushes down the water.
And that's going to push the, okay. Yeah, so you're pushing, to represent what someone just mentioned, you got your measurement of mercury, and basically we're going to say you have some like tube going into it, kind of thing. You have like a reservoir, whatever. There's your fluid, and as you push down on the fluid here, the fluid's going to rise inside the container, kind of thing. If you push down there, it's going to want to go somewhere, so it goes up it, and they use mercury because of reasons. I don't know.
It's dense.
It's dense. It is very dense. Mercury, if you didn't know, there's only 2 elements, I think, on the periodic table. Maybe there's 3. There's 2 elements in the periodic table that are a liquid at room temperature, which is kind of wild that there's literally only like 2. Everything else is either a solid or a gas. Do you all know the other element that's a liquid? So you got mercury is a liquid at room temperature. There's another one. Oh, iodine. Okay, maybe there's 3.
Iodine solid, but you're close.
Oh, iodine solid. Sorry. It is bromine. Bromine is like this crazy. If you ever like watch any videos of bromine, bromine's nuts because like it touches the air. It's like this dark reddish liquid, and when it touches the air, it like emits this like. It turns to a gas really easily. Like some of it does turn to a gas, and it's like this like noxious red cloud of gas around it. It's fun to. I don't know. It looks pretty gnarly.
And then if you're in a warm enough room, gallium will also be liquid.
Gallium's a metal. You've probably seen some videos where like people stir some soup or some not soup, but hot water with a gallium spoon, and then it dissolves. And anywho, whatever. It has not like just fun facts. Yeah. Okay. So anywho, if you all are ever given millimeters of mercury in a problem, 1 millimeter of mercury is equal to 133 pascals. I'm going to give you that on the test. I'm honestly probably just not going to have you do the unit conversion on the test because there's not much benefit. But
Also say for the setup with the tube, the top of the tube is vacuum. If the top of the tube was more air, it wouldn't work as well. Maybe if it was like a known volume at X temperature and pressure. But I think the top of the tube is specifically a vacuum.
yeah, it's an interesting little device, but that's the one that you all be working with. So when you all measure the pressure of someone's body, like when you measure someone's the pressure, and I think like 80. Oh gosh, you have 2 different pressures. I don't remember if we're going to talk about that. Adiabatic and not adiabatic. I don't remember the names. Yeah, that's a different one. Anyway, there's 2 different pressures you all measure. You know this better than I do. The value you get, I am pretty confident, is in millimeters of mercury. You don't even mention the units, but they're like attached to it. If you say someone's blood pressure is 80, it's 80 millimeters of mercury. No one just adds that unit to the end for reasons. I don't know why. All right. Something really, really, really important here. A large pressure does not necessarily mean a large force. You can see that in this equation. There's 2 ways you can get a large pressure. Sure, one way is getting a large force. What's the other way? Small area. Like, that's a thing. There is one last unit for pressure that you're not going to use in this class, but it's one that you are very familiar with every time you all fill your tires. PSI. Do y'all know what that stands for? Yeah, it's pounds per square inch. If you look at the units, pounds is a measure of force. You're like, no, remember, pounds isn't mass. Pounds is how much gravity pulls stuff down. Inch squared is a unit for area. Oh my gosh, it's the math. Force divided by area. PSI literally means how many pounds are pushing on every inch squared of your object. That's literally what it means. When we talk about newtons per meter squared, how many newtons per meters squared? How many millimeters of mercury? That's too complicated. Oh, atmospheres. Oh, goodness.
There's another unit, and that
Yeah.
there's actually 2 other units. There's atmospheres and bars, and a bar is almost but not exactly 1 atmosphere.
Yeah, oh my gosh, there's so many units. You don't need to bother with atmospheres. Though, fun fact, what is 1 atmosphere? It's literally what you're feeling right now from the air around you. It is the pressure due to the entire weight of the atmosphere resting upon you. It is not 0.
I forget exactly how many pascals a bar is, but it's more than you'd expect.
Yeah, again, why are there so many units? I have no idea. I haven't Googled it yet. Ask ChatGPT. Okay. Look, medical problems. Wow. The aqueous humor. I have no idea. I think is that the liquid in the eye based on context clues? Nice. Someone nodded their head. Aqueous humor in a person's eye is exerting a force of 0.3 newtons on the 1.1 centimeter squared area of the cornea. What pressure is this in millimeters Hg. Is this value within the normal range of pressures for someone in the eye? I have no idea the answer to part B. You'll have to Google that. I'm not going to ask you that in a test. This isn't a medical test. 10 to 21. All right. Sophia says the normal ranges are 10 to 21. How did she find that out?
I looked it up last night.
She looked it up last night. I mean, I'm not going to give you a question like that in the test. Is that healthy? That's not this class. But it makes it interesting. I can answer you from over here.
Well, so is it just 0.3 over the centimeters and the meters?
Yeah. How do you convert the centimeters to meters, though?
Just move the decimal, but now you're making me think that's not correct.
Do you just have centimeters, or do you have it?
Centimeters squared.
So you got to do it twice. You got to convert because
I want meters.
yes. So you got to convert the centimeters to meters and then centimeters to meters again. You have to do the unit conversion twice because you're not converting just centimeters to meters. You're converting centimeters squared to meters squared. So you have to get rid of both of the because it's centimeters times centimeters.
Yeah.
You got to move the decimal place.
So do I then figure out centimeters to meters, and then do I just square to get meters?
You won't square. You'll just do it once and then do it again. So, like, how many decimal places would you move it to go from centimeters to meters? Do it again. Yeah.
Explains why I got the wrong number.
Yeah. The way you can think about that is think about how you would get centimeters squared. You would multiply. Let's say you did 1 centimeter by 1 centimeter. That'd be 1 centimeter squared. But if you did, yeah.
Oh, and then meters is twice too.
Yes. Yeah. Yeah. It's easier to sometimes see written out. Yeah. So really, the key to this problem is you all got to convert centimeters twice.
So like, are we supposed to be using meters squared and
Yep. Because it's area. Area isn't just meters. Area is meters squared.
So when I times it the first time, it removes the second power?
So yeah, I'll write it out. All right. What are we solving for? We're solving for pressure. Now here's something that's slightly unfortunate, and this is where you got to be careful. You got density and you got pressure. Make sure your P's look like P's, and make sure they look different. Otherwise, you will mix them up. It's very subtle, but this is why your rows should be like at a slant with that. Just it's a notation thing. If your notation isn't clear, it's easy to mix stuff up. So we're solving for pressure. That's a capital P. Make certain that it's straight and it's got the nice little thing at the top. Yeah, I'll give you all the unit conversions, and if I don't, just ask me, and then I'll tell you in case I forgot or something. But I'll do my best to give you all of them. I do not need you. Okay, let me rephrase that. I will give you unit conversions. I will give you millimeters of Hg to pascals. I will not give you centimeters to meters. Yeah. So metric conversions, like you all need to have those in your note card if you are afraid of forgetting them. But like millimeters of mercury to that, I'll give you. Liters to meters, I'll give you that. All that good stuff. Okay, so we got our force, that's 0.3 newtons. And then we have our area, which is 1.1 centimeters squared. And so you all need to convert centimeters squared to meters squared. How are we going to do that? So I'm going to do it the way that you all do it, because again, I think this method is nice and visual. We're going to multiply this. I need centimeters on the bottom and meters on the top. How many centimeters are in 1 meter? There's 100. But here's the problem. If I leave this as is, did I get rid of both of my centimeters squared? No. So you need to do this twice. You know, another way I could show this to you is you got to do it twice. By doing it twice, centimeters is squared. Another way to prove this to you all, if I did like 1 centimeter by 1 centimeter, that would be 1 centimeter squared. Yay. If you all wanted to convert this to meters squared, you would do 0.01 times 0.01. You'd have to convert it beforehand twice. So you'd get 0.0001. 1, 2, 3, 4. Because the units are squared, you have to do the unit conversion twice. This is like a classic that people miss. So just be careful on this. So 0.00. The other easy way to do this is you just realize instead of moving the decimal places 2 places to the left, do it 2 places to the left, and then do it 2 places to the left again. 4 places. Going from centimeters to meters, you just hop the decimal place 2 times. If you're doing it twice, do it twice. Awesome. All right. The rest of this is really easy. Pressure is force over area. Really, this question is just practicing the equation and then practicing converting 0.00011. And you get a super high pressure. Is the force that large? No. 0.3 newtons is like nothing. 0.3 newtons, gosh, I don't even know what to compare it to. Let me just do some quick math. That's something that has 30 grams. That's the force of gravity of something that has 30 grams, which is like nothing. Whatever. But yay, we get the answer, 2,227.27 pascals. Now it wants it in millimeters of mercury. If you all jump back to last slide, there's 133 pascals in 1 millimeter of mercury. So we are just going to divide this by 133. If we want millimeters of mercury, it's going to be that divided by equals 2,000. Yeah. So pressure is how much force per unit area. And what we're going to learn is that the fluid applies this pressure everywhere. Everywhere this fluid is, it's pushing this. It has this pressure. And there's some cool stuff we can do with it. So yeah, it's not a force, but you could find the force on an area. So if you want to convert it to force, you need to multiply this pressure times an area.
So you know how you know like a bath, I'm sure like filling it with water.
Yeah.
Filling it with water and then pop.
Yep.
Like, is that like because the bag has a certain amount of like pressure that it can withstand?
That's a good. So the question was, you're filling a thing with water, and eventually it pops. So that's a couple things. One of it's that water can't be. We're going to learn that fluids can't be compressed. Like you all, and this is something I'll try to convince you all. If you have a fluid, you literally cannot squish those liquid molecules closer together. It's just not a possibility. It's one of the really important things about fluids. So the result of that is, as you fill a water balloon, what's basically happening is it's taking up more and more space. And so the elastic is just going to get stretched way more and more. And there is technically like a pressure, but I don't know if I would necessarily call it a pressure there. It's more so that the elastic is going to get stretched, and it can only get stretched so much, just like a rubber band if you stretch it enough. Yeah, shaking a soda can is a really good example. If you shake a soda can, you're going to increase the pressure because some of the gas will leave it. Gosh, what's another example of this? Have you ever seen those like pump rockets that like the kids have where they'll like pump something up and then like release it and it'll go woo, it'll fly up into the air? That's another way to kind of look at this. You're increasing the pressure, and then that pressure is being applied over a small area. And so you get some amount of force from that. But yeah, we'll do some problems where we'll actually calculate the force. Like we did here. Well, this one we found the pressure, but we'll find the force and find some applications of that.
Why can you compress gas and not liquids?
Oh, you can't compress gas. Oh, sorry. I thought you meant like gas, like you poured in your car. And I was like, no, you can't do that. Gases there's a lot of empty space between them. So you can squish them together because there's actually empty space. And fluids, yes, they're not like stuck together, but they're also still kind of close enough that you can't quite squeeze them together.
If you compress a gas enough, it will turn into a liquid.
Yeah.
But aren't there like there's a few liquids that you can compress them to become a solid, right?
Yeah, so if you do play around with pressure, if you do play around with the pressure of something, you can kind of sort of turn it into a solid. There's really interesting diagrams of this. They're called phase diagrams, where you have pressure and you have temperature. And depending on your pressure and depending upon your temperature, you can change the state of matter. It's not a guarantee that if you put pressure, it'll turn into a solid. It really depends upon the temperature you're at and the what substance it is. There are some things that even if you apply a high pressure to, they don't turn into a solid. So a good example of this is helium. Helium is very difficult to turn into a solid, like really difficult. Yeah, I mean, I think at some point you could.
You have to be, even liquefying, you have to be at like 2 Kelvin.
Yeah, it's silly. So helium is one of the things that, like, temperature-wise, I can give you that number. They use liquid helium in MRIs and things like that. If you are familiar with the Kelvin scale, Kelvin is absolute zero and all that jazz. Helium turns into a liquid at 4 degrees Kelvin. To give you all a sense of 4 degrees Kelvin, I think it's like 500 and something negative 500 and something degrees Fahrenheit. It's negative 269 degrees Celsius. Liquid helium is stupid cold. But yeah, even if you pressurize it. Yeah, so it's a weird thing. But yeah, fluids, they can't be squished together. Even though if you like have played with a water bottle and you've like squeezed a water bottle and you're like, I can squish a water bottle. That's because the other parts of the water bottle literally deform. Like you all squeeze a water bottle, the top part of it like goes outwards to make space for that.
And usually there's a bit of air in it.
Yeah, and usually there's a bit of air in it. But any fluid, if it was like in a rigid container, you can't squish it. This is how hydraulics work. This is how your brake system works. Your brake system, I've never done this, but if y'all ever change your brakes, one of the things you have to be super careful of is that there's no air in your brake line. Because when you all push the brakes in your cars, assuming it's not all done electronically, things nowadays are different, but most cars, there's literally a fluid line. It's called a hydraulic line, but it's just a tube filled with brake something. What's it called? Brake fluid, I'm going to say, probably. And there's a tube of brake fluid that runs from your pedal to your brakes. When you push that pedal, the fluid cannot be squished. So when you push it, the fluid inside it gets pushed, and then eventually that pushes your brake pads onto your rotor, I think, or something. If there's any air in your brake line, when you push it, that air will get compressed and your brake pads won't move at all, because instead of the fluid actually like pushing your brake pads, the air just gets compressed and then your brakes don't work, and it's really, really dangerous. They call this bleeding your brake line. Yeah, you just gotta, you have to like get in there and you have to make sure all the air is out of it, because if there's any air in your brake lines, your brakes will not work. Because the whole principle is that when you push your brakes, the fluid can't be compressed. So it like transfers that force from your foot immediately to your brakes. But if there's any gas, it just squishes the gas and does nothing for you. So, I mean, if you just cut the brake lines, then yeah, there's no fluid line, and yeah, that's gonna be really bad. All right, so again, now that we've talked about pressure, we're going to explore a bunch of, there's so much cool application to fluids. that you all don't need to know, but I'm going to teach you various things. I have 50 kilograms of water inside a large container. What is the magnitude of the force pushing down on the bottom of the container? Don't overthink this problem. You all know how to do this. I have taught you how to do this. If you want, draw like a free body diagram or something if you really want.
Oh my god.
Technical difficulties.
Oh, that was really fast.
The next two slides are to teach you all something kind of really cool that most people don't realize.
Atmospheric pressure.
How do y'all calculate? So what? Why is it pushing down on the bottom of the container?
Oh, gravity.
How do you calculate the force of gravity?
Oh, hold
And
on.
that materials level is
Oh my god. Acceleration.
For some reason, I thought you could
How are we using not negative
Because I already said it's pushing down. Magnitude means absolute value. Yeah. Yeah.
Alright, so we have
All right, 10 more seconds or so. Look how few people there are, even online. Like our class is like 90 students or something. I don't. Well, yeah, some amount of students might have dropped it at this point, but not that many. Well, if the first test went really bad, that could be why. Some people might get gotten scared off.
Yeah, they didn't have the time to put the effort in.
Yeah, it's one of those. I hope the second test goes much better for everyone. All right, we'll close it out in 5, 4, 3, 2, 1. All right. Why is it pushing down? Like, what? Well, I did say so, but I mean, one of the answers is 0, so it doesn't have to be. Yeah, it's gravity. How do you calculate gravity? Y'all got this. You can be really confident about this answer, right? And it's going to be mg in this case. Yay. So 50 times 9.8. The answer is positive because it says magnitude. So great. Okay. What equation relates area, height, and volume of an object? If you want to find the volume of an object, how would you find it given an area and given a height? And you can always play with the units to see which of these gives you the right units. Like that's always dimensional analysis is what they call that, which sounds really fancy.
It's kind of like black
Oh,
magic.
did you write that on the board?
Yes.
Okay, I was gonna say you missed that before.
If you pay attention, you can just
What is 1 bar from?
it comes up a lot in atmospheric stuff. I don't know the etymology of it.
Yeah, because I'm like, why did they come up with something different than atmospheres if they're so similar? Do you think they just took atmospheres and said that? I was gonna say, did they just take atmospheres and say I don't like this and round it? I think that's what they
I
did.
believe it.
Yeah. I totally see that. I mean, yeah. I have no idea what I'm teaching in the fall. 0 clue. I know registration opened. I have received 0 information about what I'm teaching in the fall. I have no idea. Like, I don't even know. It's done on a department by department basis. And, yeah, it's,
I still don't do it.
I don't know. I've done scheduling. I do scheduling for the TAs, and I know it's a pain. So, I don't know. It's, that is the ideal. It's not a fun process because some people are doing research and some people are sabbatical and whatever. All right, 5 more seconds. Like, this is overkill in time. 5, 4, 3, 2, 1. Nice save. All right. So if you have some volume. Oh. If you have some volume, look, here's a container. Yay, it's a tube. So fun fact, this is a really easy way for y'all to derive the volume of a cylinder. You don't need to derive the volume of a cylinder in this class. But if you all know the area of like this, it's a, what's that shape? Yeah, it's a circle. It's pi r squared. And then the question is, how many circles do I have? This is going to sound kind of stupid. You have h circles. So how do you find the volume of this thing? It is going to be the area times h. So like if you were doing the volume of a cylinder, it would be pi r squared times h. Like, ta-da, you derived the volume of a cylinder. It's the area of a cylinder. It's how many circles do you have? I have pi r squared for one circle, and then I have h of them. You can imagine them like you stack them on top of each other until you get to the top. All right, great. Why did I do all this? Because my hope, you don't need to know this. This next slide, actually, I'm going to kind of do it. I'm going to write it out because if I show you all the next slide, it's probably going to be, anytime I show you all the whole derivation at once, it's kind of overwhelming, I think, for people. All right. Rho is mass over volume. Hopefully we're all cool with that. That means that mass is rho times volume. Again, nothing crazy. Just move stuff over. And then you all just proved that you all know that volume is area times h. So that means that mass equals rho times area times h. Nothing crazy. It's the stuff that you all just plugging things in. This is how you derive stuff. You take some relationships and you plug things in. All right, awesome. Rho equals force over, it's not rho. Pressure equals force over area. Hopefully we're cool with that. What is the force going to be? Well, you all just told me if you had a fluid, that it'd be mg. If you had some fluid that was like in a tank or something, the force of gravity is mg. Awesome. You plug it in. All right. Now what I'm going to do is I am going to take this term right here, and I'm going to chuck it right there. I'm going to take the mass, rho area times h. And what do you end up getting? You get that rho times area times h times g. What's going to happen to my areas? They cancel. So what's the punchline to this whole thing? The pressure at some depth. The pressure at some depth in a fluid has no dependence upon the area of that fluid. And that's, let me give you all a kind of an example of this. If I had a straw that's 10 meters tall, filled with fluid, it has the exact same pressure at the bottom as a swimming pool or the ocean 10 meters down. It doesn't matter the area. It doesn't matter anything like that. All you care about is how up or down you are. So the pressure at the bottom of a 10-meter straw is the exact same pressure at 10 meters down in the ocean. Exact same value.
But is it the
the density of the water? Or-
Yeah, this is the density of the fluid. Density of the fluid. So yeah, this is super important. This is the exact same derivation. It's just nicer looking, but it's all there, and I worked through it kind of slowly. You don't need to know how to derive it, but there you go. As you get deeper, the pressure increases. It doesn't matter what the shape of your container is, though. A straw, a big old tank of water, the ocean. Just to draw a picture of this. So here's my straw. Here's a big old tank of water. And then, I don't know, the ocean. Woo! If all of these are filled with fluid, so if all of these are filled with fluid, fluid, the pressure at this green point is the same. Same pressure. You don't care about the container. You don't care about the pressure is the same. And I don't know what happened. It clicked a thing. It's a really, really cool finding. It's something that you all don't expect. It's something that most people don't realize. Something that's really interesting about this, when you are drinking through a straw, the way you're drinking through a straw is you're like changing the pressure. You're decreasing the pressure in your mouth, and then the pressure from the atmosphere pushes on the liquid, and it whatever goes on up. If your straw is a certain size, you can't actually suck the liquid up through it because it's too difficult. If you all try to like drink from a straw that's like 2 or 3 stories, it's impossible. Yeah, so what does pressure have to do with decompression sickness? So when you're in the ocean, let me think through. Your blood absorbs gases. So you breathe in some air, and then your blood kind of takes on that air, and some of it gets dissolved in your bloodstream. Now, what keeps it dissolved has to do with like the pressure around it. Like there's some relation with like the pressure around it kind of keeps it dissolved. Another good example of this is like when you'll open a soda can. Inside the container, all the gas is inside the liquid, but the second you all like pop the lid on the can, you've now released some of the pressure out, and so the gas like comes out of the liquid. So when you all shake up a soda can, it doesn't start fizzing in the bottle that much, but the second you pop the lid, you release some of the pressure, and now all of it can come out. Decompression sickness is the same thing. When you all are deep down in the water, there's an external pressure keeping all that gas kind of dissolved. But as you go up, that gas is now free to escape. And if you don't go carefully, it will escape. I want to say the word violently, but not violently. But it'll start to leave your bloodstream, and the quickest way out of your bloodstream is like through your skin and stuff like that, and it's really gnarly. And it like everywhere in your blood, all the gas is kind of trying to escape, and that just causes a whole bunch of unpleasantness. So, yeah. And the reason that gas was able to, so the reason this matters is your gas tank when you're scuba diving, it's pressurized air. So there's a pressure when you breathe it in, you're breathing in pressurized air. But again, as you go up, you have to go slowly to let that gas kind of escape from your bloodstream. So, yeah, and different gases, I guess, do different things.
Like 2 stories up, is that because the water boils?
No,
It's actually the thing that's forcing the water up the straw is atmospheric pressure. So if you have 0 pressure at the top and atmospheric pressure at the bottom, there's some limit to how high the atmospheric pressure can force it.
Yeah, so that's kind of a weird idea.
The weight of the water itself counterbalances, and it can't be forced any higher.
I didn't know, because like I know like the phase diagram.
Oh, yeah. No, there is, I think I've seen some stuff like that where, yeah, if you do decrease the pressure enough, it can start to boil. Like, I think I've seen cases of that. Someone did that where they're like, okay, my body can only decrease. So, again, something really weird. When you all drink from a straw, all you're doing is giving a lower area of pressure at the top of the straw, and then literally the weight of the atmosphere is then pushing the there's a difference in pressure between the two ends, which, so here's a straw, here's your cup, here's some water. The atmospheric pressure is pushing down here, and at the top of your straw, there's also an atmospheric pressure pushing down on it. That's why normally the fluid, just chills right there. But if you all decrease this pressure, then this pressure is smaller, which means the force is smaller, which means some of the fluid, there's a difference in force, and so the fluid will go up the straw. But you yourself can only decrease that pressure so much. You're basically serving as like a vacuum cleaner where you're pulling the air out of it, and if you all pull some of this air out, you decrease the pressure. You can only do so much of that, but even if you all hooked up like a really strong pump, at some point it does start to actually boil, which is kind of weird. I mean, I guess you're still getting the liquid just in its gas form. Anywho, cool stuff. Great, let's see if it makes sense. How does the pressure at the bottom of a 10-meter pool compared to the pressure at the bottom of a 10-meter tall straw? Both are completely filled with water. That's really important. They both have to be filled with the fluid all the way, and the same fluid. So is the pressure at the bottom of this pool greater than the pressure of the straw? Is the pressure of the pool at the bottom of the pool less than the pressure of the straw? Are they the same, or are both pressures 0? We're talking at the pressure at the bottom of both of these objects, to clarify.
You said the straw was 10. Is it 10 or 12?
Oh, the straw is 12. Now, if you all wanted the force, you would need to take this pressure and multiply it by the area at the bottom of this object. But we're not talking about force, we're talking about pressure. Two different things used for different applications. It's a very large straw. It's a lot of straws tied together.
That'd be crazy. The ultimate silly straw.
Yeah, again, there is, I mention this all the time. There's a really good YouTube video. You all can look this maybe I'll try to find it, where someone does try to see the limit for how tall the straw they could drink out of. I forget how high you could get. I'll look for it during the break if I remember.
The pressure of the straw is equal to the bottom of the pot, right? Bottom, top.
All right, give y'all 5-10 more seconds.
It would be unstable, but it would work exactly how it ended up.
All right, in 5, 4, 3, 2, 1. All right, so how are we going to answer this question? What are we solving for? Pressure. What's the equation for pressure at the bottom at some height? It's rho GH. Does the density of the fluids change between the two examples? No. Does G change between the two examples? No. Does the height change? Yeah, the one with the larger height wins. So the pressure of the pool is less than the pressure of the straw. The height of the straw is greater than the height of the pool. Now, if you're but what? But there's so much more water. Sure. If you all really want, the force at the bottom of the pool will be bigger than the force at the bottom of the straw. That will be true. Why is that true? Pressure equals force over area. So if you have a bigger area, you get a larger force. So if you want the force, you rearrange this, you get that. Awesome. So like if you all have a pool, the force on the bottom of that pool, like on that membrane on the bottom, it's decently large, but that's spread out across the whole area. What's a consequence of this? Why do we care about pressure? We're going to learn that if like you filled these two things with water, say you like had a pool and you like poked a hole at the bottom of it. I don't care how big this hole is. But then you have the straw and it's the same size hole. The water that leaves the bottom of the straw will go faster than the water that goes through the pool. Pressure is how we're going to relate to the velocity of the fluid. Like if you let all this water drain out of the straw and you got the same size hole in the pool, the water would leave much faster. Well, somewhat faster, which is kind of cool. Pressure only depends upon the height. That's really what I need you all to know. Super, super important thing. How does siphoning work? Siphoning works the same way as a straw. You decrease the pressure, and then so if you all have a fluid up here, this is not something you all need to know. If you all have a fluid that's up high and a container down here, if possible, the fluid would like to go here because it's a lower energy. But the problem is, if you to siphon something, you stick a straw. Woo! There's your straw. Here's the problem, though. If you all want to make this fluid go from this tank to this tank, notice that straw originally goes up. So how do you make it start moving? You pull you start breathing. You decrease the pressure like a straw. You decrease the pressure. As the fluid starts to travel up here, you get something called surface tension, and that surface tension kind of keeps pulling it along. So you kind of got to get over this little hump first. Once you get over that little hump, once you get the fluid over that hump, the surface tension kind of keeps pulling it along. Because ideally, this water would love to go down here because it's slower. But you got to overcome this initial little hump. And so that's what, when you kind of like get it going, that's what you're doing. You're getting it moving over that little like extra little bit. It's got to move up. And then after you've done that, the surface tension kind of keeps it going. So it's a little more complicated, but yeah. So many fun fluid things. Okay. What's the consequence of this? When you all measure someone's blood pressure, where do you do it? Arm. Why? It's level with your heart. So when you all take someone's blood pressure measurement, you are actually trying to measure their blood pressure at their heart. The only thing that matters is to make sure you're measuring at the same height as the heart. If you all draw a straight line from where you measure the blood pressure, it's the exact same height as the heart. If you all measured if you had their arm up in the air, you'd measure a lower value. If you measured their arm and it was like hanging down, you would measure a larger value. Literally because of this equation. So let's do this problem. Suppose you measure a standing person's blood pressure by placing the cuff on his leg 0.5 meters below the heart. Calculate the pressure you'd observe in units of millimeter of Hg if the pressure at the heart were 120/80. Assume that there's no loss in pressure due to resistance in the circulatory system. Whatever, don't worry about that statement. The density of blood is about 1.05 times 10 to the 3. It's a little bit more dense than water. My guess is that blood is mostly water. I'm pretty confident in that. But with other junk thrown in. Yeah. White blood cells, red blood cells, platelets. I don't actually know what plasma is. You all probably know it. I don't know what the chemical composition of plasma is. I assume it's mostly water with, again, junk thrown in. Yeah. Who needs it, right? Oh, and the reason you all probably already know this. The reason there's two blood pressures is based upon when your heart does its little pump that makes a spike in blood pressure, and then after a little bit, there's like a delay, and that decreases it. So you have like a high and a low from I had to look. I didn't know any of this stuff. I don't know medical things.
Systolic and diastolic.
Yeah, that's probably sounds right. That was-
Systolic is the loud, not the one loud.
yeah. And I think what I learned is that those are based upon when the heart originally pumps, you get the highest pressure, and then after some time, it's the lowest pressure. Yeah.
So when you're listening and you do it manual, what you're listening for is like when it starts pumping again. So you squeeze the cup and you don't hear anything.
Oh yeah, and then you wait till the blood starts flowing or something. Yeah, I heard. Yeah.
And then when it starts pumping again, that's your systolic, and when it stops, that's your diastolic.
Okay. Yeah. So yeah, hopefully you all probably learned how to measure blood pressure, but now you actually know what you're measuring. You're measuring the force per unit area.
Human error will make it.
Yeah.
Is it like negative 0.5 because it says below heart pressure?
Oh, that's a good question.
If anyone needs the unit conversion, have it here.
So-
I'll put it up there as well.
That's like pressure and height would be negative.
No pressure.
No, you're not necessarily going to do the negative here.
There's two pressures too.
It kind of depends upon how you choose to frame it. Your pressure will be higher. So no, yeah, put a positive. Put a positive here. Yeah, someone had a really good question because we're so used to potential energy, which is awesome. Like, do we put this as a negative? The answer is no. This one you're going to put as a positive. And the way to remember this, as your height increases, as you get farther down, does your pressure go up or down? Up. As you all get farther down, your pressure gets up. So we're just going to kind of use a positive here. You will never have a negative pressure. Negative pressure is a weird, it's technically possible, like in trees. Yeah,
That's not really, that's like a
I think I've heard people mention there's true. Yeah, it's. Don't worry about it. I've heard people mention this. Don't worry about it. Yeah, that's one of those things I've heard, but I don't know enough to actually talk about more.
I think there's not actually real negative pressure. I think it's just
Let's go with that. Let's go with there's no such thing as negative pressure and just move on with our lives there.
So if pressure is equal to height times gravity times density, we have density, we have height, we have gravity, doesn't that just give us our that pressure?
I just averaged it out.
Yeah. So. Oh, you should have two different answers here. These are two different blood. So this 120 over 80, this is your all's lingo. This is medical lingo. Let me write this as a given. You all have two different pressures. I'm going to call this pressure high and pressure low.
It's systolic over diastolic.
So this 120 over 80 does not actually mean division, which boo to medical stuff for using this terminology because it seems like it's a division problem. I don't know why they say 120 over. I think they should say 120 high, 80 low. That sounds way better to me.
People do, it's just how you write it.
Oh, really? Some do say high and low?
Yes.
Oh, great.
When you're writing it, it's easier to just say 120.
Sure, and that totally makes sense. Yeah, but medically, yeah, people for shorthand say 120 over 80. These are two different pressures. This is a measurement at some point. This is like the highest blood pressure your body experiences, and then the other one is the lowest blood pressure your body experiences. They're two different measurements. So you all are going to calculate two different pressures here. You're going to do the problem twice. One for the high measurement, one for the low measurement. But do them separately. I'm not going to give you all a problem like this in the test where you need to have medical context knowledge to answer the problem because I don't want you all to miss points because you didn't know medical things. There are some IT majors in here.
Not bad, actually. But it is much bad. Or she has no clippers in my bag. Yeah, I know, but I'm also a nail dealer, so I get it. It's the worst thing. I always try to wash my nails. Actually, not that. I just had fake nail polish. I put them on.
Pressure is this much at, how much is it?
How do I?
So you have.
How you
So it isn't that bad. I'm just as small because I don't understand
So.
what these numbers have to do with that.
We're at, some pressure, on the,
We would not know.
how much, what pressure?
It was just like, it was really funny.
What pressure would be achieved?
No, I know, but like.
What's up?
So, I just want to understand this. So, I'm guessing we're using the equation we put over, which pressure equals that, yeah. So I did the density times the low heart and then times by gravity, and I get this number. I don't know what that number is. What is that in units in?
So that's going to be in pascals.
It's in pascals?
Yeah.
So I'll divide that by 133.
Because we're using the density of blood given in kilograms per meters cubed.
So that'd be 30. And so I would add that.
Yep. All right. So let's think through the logic here. At your heart, we measure the blood pressure. 120 over 80, whatever. Two different measurements. What happens to the pressure when you go farther down in the body? Is it going to go up or down? It's going to go up. How much is it going to go up? How could we calculate how much it's going to go up? What equation would tell us how much the pressure is going to go up? It's the one on the board. Pressure equals rho GH. This tells me that due to gravity, my pressure is going to go up. Now, gravity is not the only thing in this problem. There's also the heart and So how are we going to solve for these? If you all want to know the pressure, we're just going to take that and add it to the original. The heart adds some pressure. That's what we are given. And then gravity adds some. Basically, again, the question is how much did it go up by? Find that and then add it to the original. That's the whole purpose of this problem. There is some blood pressure in your body because the heart increases the pressure. And then your blood pressure is different at various points in your body due to the height as well. So the total pressure is going to be the one due to gravity plus the pressure due to height. The total pressure at the lowest point will be the same exact thing. All that we're doing is adjusting the blood pressure based on height. If you will instead measure the blood pressure at the top of the head, would it be up or down? Would I be adding or decreasing? Decreasing. So that's one thing. If instead I said, find the blood pressure at someone's brain, you'd find the distance between the heart and the brain. And instead of adding it to my original pressure, I would subtract it. So yeah, at this point, then the last thing you all got to be really, really careful of. When you all calculate this, it's going to be in metric units. You all got to convert it to millimeters of Hg if you want to add them together. So, whatever. I'm just going to leave this here for now. And then the total pressure is going to be the pressure due to gravity plus the original pressure, whatever. All right, pressure due to gravity is rho GH equals 1.05 E3 times 9.8 times 0.5. What does that equal? I don't know. 5,145. What's my units? Sorry, I missed it because I coughed at the same time. If you all do this math, what units does it kick out? Pascals. You cannot just add pascals to millimeters of mercury. Your blood pressure 0.5 meters below your heart is not 5,265. Like, do not add that number to 120 and say that's your blood pressure. Like, hopefully you all realize that number is insane. No one's blood pressure is 5,200 millimeters of mercury. That they're dead. They're like so dead. Like every single one of their blood vessels blows up, and it's awful. How many pascals are in a divided by 130? Do. How do you make sure you don't make this mistake? You just look at the numbers and say, does that make sense? It does not make sense for someone's blood pressure to be 5,145.
I don't know. It's standard, but also like it is the same thing as writing as
All right, so if y'all want P total, you just take this and you add it to each of the values. If you want the total high blood pressure, there's the name that someone else said that I already forgot. Systolic. If you want the systolic one, you add the one that you measured at the heart plus this increased value. If you all want the other word, diastolic, you take that number and you add it to this value as well. So there you go, 158.68, which, there you go, and then 80 plus this. And I'm pretty sure if you all measured these values, it'd be very bad, I think. I don't know, what's unsafe?
More than that.
That's really bad. So, make sure you measure the blood pressure parallel to the heart. Because if you don't, you're accounting for the fluid itself increases. So yeah, your all's blood pressure near your legs and at the bottom of your feet is a higher value than it is near your heart. Literally because the weight of the fluid is above it, is affecting it. So there you go. All right, take a breather. We'll reconvene at like 9:30 on the clock. I'll blow my nose. It'll be a great time. Ugh.
I thought one of the microphones was missing, but it's not.
Yeah, this fluid stuff's fun. I was like, you never actually get to cover it though in any physics class.
Yeah, I got 0 fluid mechanics.
Same, absolutely zero. I had to look.
The first time I saw Navier-Stokes was in differential equations.
Oh my gosh! Now you're still. What is that even used for?
It's like the fluid mechanics equation.
Okay.
It's like,
what does it account for?
It's some partial differential equation with like pressures and forces.
Does it account for viscosity?
Yes.
Okay, that's what I was.
I think.
Yeah, everything we're doing here is neglecting viscosity. That's why I was curious.
I mean, it just came up briefly in a different class.
Sure, I've never seen that one. We're obviously not going to cover that one.
Or the only one, please.
I like older. 6 a.m. to 12 mornings.
Nine? It's hard to do the math. It's like, right, so it's 4.
Yeah.
It's a lot of you.
It is a lot. It is a lot. Yes.
Oh my god.
Okay, wait. With
Is the lab online too?
okay, so hold on. Yes, okay. So listen, it hurts. Listen, but like honestly.
Like I didn't one of the like lessons
So she's very nice. And what she does is like the lecture and the lab, like one. So and so it's not like they're separate and there's separate exams, but for her exams, it's like she does my exam, they just have questions from both.
So assuming I plugged the correct thing into Wolfram Alpha, the tallest possible straw should be a little over 10 meters.
Oh yeah, let me look up that.
It's assuming zero pressure at the top. The tallest realistic straw is going to be shorter.
Yes, but like it's just because she's there.
But at least it's not like, yeah, it's not like that.
Like 10%, 10 to 20% are lab questions. The rest is all lectures. But she like these like lecture videos.
We don't have anybody else. They do.
I like this guy a lot. It's the Action Lab. Oh, sorry. What height did you say?
I said 10.3 meters.
And is that because it starts to boil away?
Top. No, that was just pressure versus weight.
Okay. I know you do run into the problem like Justin was mentioning. It does start to boil.
Yeah.
So even if you had the strongest pump possible.
Start to become significant around what the vapor pressure, water pressure at the top.
That's a good question. I don't even know. I don't even know what Matthew. I'd have to look at a pressure volume diagram. I'd have to look at a temperature given a pressure. Does water turn to a gas?
I know, like from chemistry, there's vapor pressure. This is just how much pressure there is on the surface of the liquid exchanging with the air.
I don't remember learning that. I'll trust you on it.
And boiling is when the vapor pressure is equal to the surrounding pressure.
There's only so much you can cover. So, like, technically, we're also supposed to cover thermodynamics. Can't cover, gosh, where would I fit that? Because we still got to cover circular motion and everything on that. I have to update those. Yeah. It is technically only 2 weeks left. I need to update those PowerPoints though. We have a decent amount left to cover because we need to cover all the rotational variables. So theta, omega, which is W, and alpha. I need to cover centripetal force. Yeah, we skipped that because I was going to do it here at the end. And then we got to use the rotational variable, like the rotational kinematics, which is just the normal kinematics equation, just with all spinning stuff. I need to cover torque, which is like force, but for a rotating object. And then torque equals I alpha, which is Newton's second law for a rotating object. And then I got to cover angular momentum. Yeah. I figured that would be the case. Yeah. So basically, everything that we've learned with kinematics, everything we learned with translational motion, I got to teach the rotational equivalent. The nice thing is it's the exact same setup, just with different variables. Instead of F equals an A, it's torque equals I alpha.
torque is like force. Instead of all the kinematics equations, you just plug all the other things, like rotation variables. Instead of momentum equals m times v, it's rotational angular momentum equals I times omega. My dream, though, is that I can convince everyone it's the exact same equation you've learned with a new paint job. We'll see.
If you put it like that, I think you understand if somebody like
Oh yeah, I'm gonna say that again and again and again and again. Everywhere you see M, replace it with an I. Everywhere you see V, replace it with an W. Everywhere you see A, replace it with an alpha. And it's all the same equations. The only one that gets a little funky is moment of inertia, but they are spared because they don't have to calculate it because it requires integrals. The only one that you got a hoop. That's like easy. I think that's it.
Yeah, because if you have like a sphere or cylinder, those wind up being very simple.
I don't know how.
You'd have to, once you derive it, it's just some fraction of the time.
Oh, yeah, sure. The answer comes out really simple. But to get that answer,
Getting that answer,
that's
you can just tell them here it is.
That's what I'm gonna do. Yeah. Whereas for 2048, I actually have to teach them how to do the integral. Okay. I found the video. We're not gonna watch it now because it's 8 minutes long or whatever. Whatever. Here's an ad. Again, we're not gonna actually watch the video, but it's great. This guy is awesome. If y'all if you want to learn any science stuff, I really like this YouTube channel. And yeah, anyway, he goes through what's the longest straw. He climbs to the top of the building. He eventually hooks it up to a pump. I do think at some point he does show that it starts boiling. I don't know why he says don't try this. I don't know what's going on there. Because at some point you decrease the pressure so much at the top of the straw that at low pressures water starts to boil. No, because the temperature is the same. Yeah. If you decrease, there's two ways to make things change their phase. One is to change the temperature. One is to change the pressure. If you keep the temperature constant but you decrease the pressure enough, some things will change to a gas. Anywho, whatever. I posted the video in the slides that I upload. They'll be there. All right. I've already mentioned this, and I gave this picture of this toy because I think it shows it really nicely. Fluids cannot be squished. You cannot compress a fluid. You cannot make water molecules get closer together. If you have ever played with this toy, when you squish it, you are not making the water molecules closer together. They just then squish on the rest of the object, and you get this, weird looking thing. And something really, really important about fluids is any change in pressure is immediately applied everywhere in the fluid. Like this information, technically, it doesn't travel instant, but we're pretty darn close. When your heart beats, that increases the pressure everywhere in your bloodstream, like instantly. And then as time goes on, it decreases again, and so on. That information travels very, very, very quickly. Not quite the speed of light, but pretty darn quick. Maybe like the speed of sound or something. The molecules have to literally bump into each other. I don't know how quick it transfers, but it's pretty darn quick. Why does this matter? So many reasons. All right. Below is a set of pistons. So what is a piston? A piston is something that can kind of go up and down. And when it goes down, it's squishing some fluid inside of it. So here you can see this piston. If I push down on this side, it's going to squish the fluid in here, which in turn squishes the fluid over here. It doesn't matter that there's just a tiny little path between them. If I increase the pressure here, I increase the pressure everywhere in this fluid at the exact moment. Everywhere. It doesn't matter whether it's thin. It doesn't matter whether it's a big wall here. The pressure experienced here will be the same everywhere. Awesome. Great. So what? Okay. Pistons. You got some pistons with share fluid. They're connected by tubing and whatever. If you push down on the left piston with some force, what's going to happen to the force on this bigger piston? How do you answer this question? The pressure is the same everywhere. So use that information that the pressure is the same everywhere. Will the piston on the right experience a larger force downwards? Will it experience a smaller force downwards, a larger force up, or a smaller force up? Use what you know. Use the equations you all know. We're talking about force. We're talking about pressure. There's a really nice equation with those two things. And to give you a hint, what's the equation? What equation relates pressure and force? P equals F over A. Use that equation. If you're not using that equation, you're doing something wrong.
So it would I think it would experience a smaller force.
I think it's like if I first started out the one I don't even
It would go
So you push that one down. That's going to cause some pressure in the fluid. Make up a number for that pressure. Whatever. 2 it is. So how much pressure does this first piston experience? 2. What about the right piston?
It also experiences 2.
Use that to answer this problem. The pressure is the same everywhere in the fluid.
And then let's say we push down the forces
All right, y'all got 10 more seconds. All right, in 5, 4, 3, 2, 1. All right, so notice that both of these pistons are at the same height. So do we really care about the effect of gravity here? No. Gravity is not going to affect stuff. So great, gravity doesn't matter. Why is there any pressure in this fluid? You push on it. You make some pressure. Make up a number for it. Give me a number. 20 pascals. Great. It's a very, very low pressure, but we don't care. So let's say that the pressure is 20 pascals. PA. Oh, why are they called pascals? Because they're named after a guy whose last name was Pascal. Because he did stuff with fluids. What did he do? I don't know. I don't remember. All right. Oh, I say that. It's literally the next slide. What he did. How silly of me. All right. The pressure is the same everywhere in the fluid. So how much pressure does this first piston experience? 20 pascals. How much does the other piston experience? 20 pascals. Great. It's everywhere is 20 pascals. How much pressure is inside this tube? 20 pascals. It's 20 every, now, okay. Granted, at the bottom of this tank, it's bigger than 20 because we just talked about gravity and weight and, you know, all that good stuff. So technically, that's going to be slightly, whatever. It's the same everywhere. Why does this matter? Let's find the force. So this one, the first piston's force is going to equal pressure times area. The second one's force is going to equal pressure times area. 20 times area 1, 20 times area 2. How does the area of piston 2 compare? Is it bigger or smaller? Bigger. Area 2 is bigger than area 1. The second piston experiences a larger force. So this is something that's super cool. You can multiply your force. You all can take a force, you can apply it, and you can multiply it. Ta-da, you all discovered how hydraulics work. Have you all ever seen like construction equipment? And all that construction equipment is incredibly strong. It's really hard to get a sense of how strong construction equipment is. One really good example for you all to experience how strong construction. Anytime you all watch like a backhoe pick up a bunch of dirt, think of how many shovels of dirt it would take you to lift up that same amount. It is so much. They are picking up like a wheelbarrow's, way more than a wheelbarrow's worth of dirt with every single scoop. They're scooping in the dirt and they're picking up an amount of dirt that's like a meter squared. It's a silly amount of dirt. Think of how much work that would require for you to do the same thing. How are they able to do this? How is this piece of equipment able to lift so much? Hydraulics. They apply a force over they apply a pressure, they have some like little thing in there, and they're able to make these hydraulic pistons move, and that multiplies the force because they increase the area and all that good stuff. It's great. So this is called Pascal's principle. I just said I didn't know what he did. Here's what he did. He found that in a fluid, if the pressures are the same, you can multiply the force if you just apply the same pressure over a bigger area. Again, your brakes is another example of this. You all apply the brakes, you apply it to a small area, and then your brake pads are done over a bigger area. And so you multiply the force. So you all don't have to push on your on the brake that hard to make a force that clamps on your wheels really strong, which is pretty important if you want to stop your wheels. Like, that's really hard. If you all wanted to stop your wheels with your hands, good luck. Like, it's not going to happen. Yeah. But you all are able to do it with your foot. Literally, the force in your foot is enough to stop your wheels, which are spinning incredibly fast, because it multiplies the force. It's kind of like I don't know if y'all have ever heard the sayings. I forget who said this. Someone said, like, if I had a lever strong enough, I could lift the earth. Levers are another way you all can multiply force. We'll kind of talk about that at some point. This is another way you can multiply force. To me, it almost feels like magic that you can like take a force like 1 Newton. If you apply it to an area that's 100, you can multiply it by 100 just by applying it to an area that's 100 times bigger. Now, that other piston will move less, but we don't care really how quickly or slowly it moves. We just need it to move. So that's the trade-off.
It will move, and you're still going to get the same amount of work. So the amount less that it moves is 4 times distance, so still get the same.
Yep. So you get a greater force, but over a smaller distance. So you're not cheating physics. You're not adding more energy. Like, you're not making energy out of nothing. That's always important. But yeah, this shows up. Again, hydraulics. Anytime you all, let me just look up a backhoe real quick.
There's actually a really simple way to show that for this scenario, because you're moving the same volume of fluid. So bigger area, smaller height, same volume.
So if you just look at any construction equipment, This is a piston. There's a bunch of pistons on here. These pistons are just using this principle. They're using hydraulics. Hydraulics are just a bunch of fluids where you apply a pressure over a small area, a force over a small area, and then you have a piston that has a bigger area and that force gets multiplied. And that's how if you look at any construction equipment, you will see these pistons on it that are utilizing this principle to generate extremely large forces, which are necessary to pick up crazy amounts of dirt or break apart rocks or, do things that if you tried to do it yourself would be awful. Anytime you need a large force, hydraulics will be involved. If you all have ever seen, what was that YouTube channel called? The hydraulic press channel. The hydraulic press channel is literally how do they generate such high forces? Hydraulics, fluids, pressure, area, all that kind of stuff. Anytime you need a large force, you're pretty much always working with hydraulics, which i.e. is just this. It's so simple. It's such a simple mechanism. Just increase the area, apply the pressure over have a small area and then apply it to a big area and you multiply the force. Now, what is kind of interesting is how do you generate these? They have pumps, and the pumps generate some pressure. And then if you want a certain force, you just take that pressure and you apply it to some piston with a certain area. That's all they do. So they have some pump that generates some pressure. They then have a piston that has a certain area, and they just multiply the two numbers, and ta-da, you have a certain force. All right. Look, medical things. A syringe is just a couple pistons. Like the sound, I say a couple pistons. Let me draw a beautiful picture of this. In a specialized hydraulic syringe, which sounds really silly, it's just a syringe. A doctor applies a force on a large piston with a cross-sectional area of 20 centimeters squared, and then the medication is dispersed through a small tip with a cross-sectional area of 0.5 centimeters squared. If the doctor applies a force of 60 newtons on the large piston, what force is transmitted to the small tip? So, you all have used a syringe, I'm sure. Look, there's a syringe. It's got a plunger in it. That plunger is the piston. This is the opposite. When you apply a large force here, you get a small force here. That's the idea. Why is this useful? You want to control you all don't want a ton of fluid going into someone. If you make the force less, you get a controlled, you can more limit the amount of fluid that goes into something. Your thumb only has so much precision. This tool helps you ensure that not a ton of fluid is going into someone. Whatever. You can see that there. It decreases the force in the fluid. So anyway, try it out. It's pretty straightforward.
Big numbers for a syringe.
Yeah, it's a really big syringe. Well, I mean, how much is 20 centimeters squared? I don't know if it's that big. Oh, yeah, that's true. It is 20 centimeters. Yeah. Is it this big? I guess it's 21 by 1 centimeters, right?
Yeah.
Yeah. Yeah, it's a lot. Well, hold on. It would more so, it'd be something that's like 5 cent. It's still very big. 5 by 4. So it's, yeah, it's like that big. That's not terrible.
I don't know what I was thinking.
I'm thinking 20 by 20. Well, you're also probably thinking the same as me. 20 by 20, like something.
I think my brain was measuring in inches.
Yeah.
I'm used to things that are big enough, an inch and a centimeter are approximately the same.
Yeah, centimeters are funky. You don't work with them much.
No.
Fun fact, you don't actually have to convert your units to meters squared here. It ends up canceling out, but I did it just to be safe. If you don't know why you don't need to convert it, just convert it. The reason it doesn't matter if you convert it, if both sides are centimeter, they're going to cancel each other out. If both sides are meter, they're going to cancel each other out. But again, I like to be on the error of caution. I like to err on the side of caution. If you don't know why that's going to happen, just always convert. It's better safe than sorry. So yeah, you just divide, you just do the equation. So I rearranged it. I like to do that. So force 2 is going to be F1 divided by A1. So that's going to be 60 divided by 0.002. And then we're going to multiply that by 0.00005. And yeah, that'll spit out the 1.5 newtons. Yay! You all can also see this. If you all take the areas, the area of the syringe is 1/40th. So 0.5 divided by 20 is going to equal 1/40. There's 40.5s in that. That means my force is going to be a 40th. So if you do 60 divided by 40, you get 1.5. That's kind of like the shortcut. If you realize the ratios, it's all ratios. If the area is twice as big, you get twice the force. If the area is 5 times as big, you get 5 times the force. If the area is 1/40th, you get 1/40th the force. It all works out that way. Okay. So again, so many cool things with fluids. Just to kind of keep track, because we've covered a lot of things today. We talked about pressure. And all the fun little units in it. We've talked about how fluids weigh. They have a weight associated with them, and this results in a pressure, but it turns out the area doesn't matter because it cancels out. We then talked about that fluids are incompressible, and so because of that, you can do cool stuff with hydraulics. All right. Now we get to learn about more things. Again, it's just... And this one I'm about to teach you all is super cool because the guy that discovered it was 400 BC or something. Yeah, this one's super impressive that they came up with this. Yeah, I fill a water balloon completely with water, and then I put it underwater in the lake. Which of the following is the correct free body diagram for the water balloon under the water if it's not moving? It doesn't pop out. It's in the water. We filled our water balloon completely with water, so there's no air in it. Is it still on Earth?
Yes, so there's gravity acting on it down. And I think pressure acts up on it, because right, it's pressure up. If it's if it's water in the water.
So just think through the logic. If it's not moving, so you know there's gravity down.
Yeah.
If it's not moving, what's its acceleration? So if you picked A, which way should it be moving or should it not be moving? It should be. So then.
Yeah, doesn't pressure act up on something?
So we're going to learn that there's a new force. There's There's a
But this one wouldn't that mean
Make sure your answer makes sense
you know what I mean?
based on what you know.
Like it's because this one is like so there's a bigger arrow down, yeah, a bigger arrow going Central C. Central C. Oh no, I don't. I'm not cultured. No, that's not.
All right, 10 more seconds.
I just know you have it. All I think I've heard that one line. Probably. Like a meme.
All right, 5, 4, 3, 2, 1. 1. 1. 1. All right. Great. We draw a free body diagram. What forces are acting on this balloon? You got this balloon in water. Is it on Earth? Yeah, so what forces are always? Gravity. Great. Great. There's gravity acting on it. Now the question is there any other forces acting on it? And this might be a little tricky because you're like, ooh, I don't know. We haven't learned about stuff in water. If it's not, according to my picture right now, what should my water balloon be doing? If there's a force, if the only force is downward, it should be accelerating downwards. Is my thing accelerating downwards in this problem? No, it's not moving. So what's my acceleration then? If you're not moving, what's your acceleration?
0.
How do I make this acceleration 0 then? If I have a force downwards, what else does there have to be? You all just discovered the buoyant force. Why do things not fall in water? Because there's a force pushing upwards on it. And how do these two relate? They're exactly equal to each other. So yeah. Ta-da! And so this is Archimedes' principle. Yeah, actually, let's write this out. So the buoyant force equals the gravitational force, which means the buoyant force equals m times g. Ta-da! So this is a really cool, again, this guy discovered this, I think, in 400 BC. The buoyant force is equal to the amount of fluid, the weight of the fluid it displaces. The buoyant force is equal to the weight of the fluid it displaces. The amount that any object gets pushed upwards, a boat, literally any object that goes in water. How do you calculate the force that gets pushed upwards? It's so easy. You just figure out how much fluid got displaced, and you find it's the force of that, the weight of gravity of that. So you figure out how much mass of water got displaced, multiply it by gravity, boom, done. If it's in water. Or what other fluid it is. And the logic here is really, really interesting, and I had to think about this for a while. So here's how this guy discovered it. Basically, the question was, what if there wasn't an object? If there wasn't an object there, there'd be water there, right? Like, if there was no object there, there'd be water there. Is that water falling? No. I mean, if you all look inside, if you're inside some fluid, it just chills there, right? What's holding it up? Something's got to be holding it up. Gravity should pull things down. Why isn't it falling? Because the buoyant force. It's literally the problem we just did. Except instead, you all literally just did it as a water balloon filled with water. How much force is required to keep it up? Literally the mass of the water inside it times the gravity. Like, it comes from Newton's second law and all that stuff. This is before Newton's second law existed, though. So it's really, really cool. I think it's super, super interesting. It's such an easy calculation. So we'll practice applying this. That'll be our next kind of thing, is actually applying this. But yeah, buoyant force, how much something gets pushed up in a fluid, how much mass does it displace times G. Done. So easy. All right. One more thing I'm going to mention to y'all. And I already actually mentioned this to y'all. The fraction submerged is just the density of the object divided by the density of the fluid. And it comes from this equation. It comes from literally that thing before. Fraction submerged, whatever, velocity of fluid, velocity of object. How do you get, not velocity, volume. How do you get volume? Reminder to y'all, density is mass over volume. Therefore, volume is mass over density. I'm going to give you all a problem on this, and then let's see, how many problems? I hope I have another one here. No, I don't. All right. I'm going to steal one from the problem set. We're going to do it because I want us to practice this. Again, there's so many different, I already mentioned this, fluids has so many different things, y'all. All right, so I think this one's kind of cool, which is why I'm going to pick it. All right, a twin-sized air mattress is used for camping. Here, I'll chuck it in here so y'all can see it in bigger text. All right, a twin-sized air mattress used for camping has dimensions of 100 centimeters by 200 centimeters by 15 centimeters and blown up. The weight of the mattress is 2 kilograms. How heavy a person could the air mattress... This would be better. How much mass could the air mattress hold up if it's placed in fresh water and we want to keep the person out of the water? What's the maximum amount? And we're just barely going to keep them out of water. If there's a wave, they're going to get splashed. Thousand kilograms per meter cubed.
1,000 kilograms per meter cubed
Mm-hmm.
is the density of water.
Did I hear you say you got the volume of this was 30 meters squared?
The area.
Okay, the air.
Because don't you by the area, don't you times all the centimeters by each other?
Yeah, convert it to meters first.
But yes. Convert to meters and then. Okay.
Yeah, do the conversion beforehand.
Heard.
Yep, you are going to want to convert from centimeters to meters. That's why I tell you, it's like
Meters squared or just meters?
just convert each centimeters to meters, and then then you'll be good.
1 meter is 300 centimeters. So 100 times 1.
All right, so I'm going to draw a pretty picture of this. All right, so you got some water. Doop, 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 doop. and you got your air mattress. If we want to find the maximum amount, that means my air mattress is basically going to be completely submerged in the water. Great. Let's draw some forces on it. What forces are acting on this thing? Gravity. Oh, you got your person on it. Let's pretend like they're lying down. It really doesn't matter whether they're lying down or standing up. It's all the same. Assuming a rigid body. All right, so you got the force of gravity. Now, this force of gravity is the air mattress and the person together. Like, they're all getting pulled down, right? It's everything. Mattress plus person. Great. Why aren't they sinking? What's pushing them up? The buoyancy force. How do those forces compare? They're equal to each other because what's the acceleration? Yeah, just to write this out all official like, sum of forces equals m times a. Force of buoyancy plus negative force of gravity equals, my acceleration here is 0. Why is it 0? Because they're not falling and they're not getting faster downwards. Or my force of buoyancy equals the force of gravity. Great. All right, so whatever. We just drew a picture for that, though. What are we even solving for in this problem? It's always good to keep your eye on the prize. What's the prize? Mass of the person. What's given? Yeah, we got the mass of the mattress. Yeah, mm equals 2 kilograms. We're going to get the volume of the mattress. Anytime I give you dimensions of an object, you're going to guess that we're going to get volume or area. In this case, it's going to be volume. So it's going to be 0.1 meters times 0. Oop, that's terrible. It's going to be 1 meter times 2 meter times 0.15 meter. Yep, we're going to convert it. If you don't convert it, things are going to end bad for you. 0.3 meters cubed. Great. So what? All right, we want to find the mass of the person. We have to build this equation. So I kind of wrote it here. Force of buoyancy equals force of gravity. How do I find the force of buoyancy? What was the equation I just gave you all? Mass of the fluid times G. Mass of the fluid. How the heck am I going to find the mass of the fluid?
You have the volume of it, and you know how much density.
How can I find the mass of the fluid? Density equals mass over volume. Do you all know the density of the fluid? Yeah. Do you all know the volume of the fluid that's being displaced? Yeah. And then, great, Fg is going to equal the mass of the person plus the mass of the mattress times G. So, Fb is going to equal Fg. Fun fact, G is going to cancel out. This problem would be true on any planet, so that's kind of cool. And you find the answer.
Okay.
So I found the density of the mattress.
Yep.
And then so I divided it by the density of the water, which gave me and then so I got the specific gravity of the mattress.
Okay.
And I took the mass of the mattress, divided it by the specific gravity. I got 300. Let's do 300 minus 2.
Yeah, that works. Yeah, that all works as well. Yeah, all that works as well.
Okay,
I mean, if you got the right answer, your process is working, as long as you're cool and you know why it works and all that jazz.
All right.
Yeah. And the density of water is 1,000 kilograms per meter cubed. The density of water is 1,000 kilograms per meter cubed. Yeah, or if you need it, no problem, I'll give it to you. Yep, again, I don't need you all to have that memorized. It's kind of like the value that G is 9.8. I technically give that on the test. You'll end up using the density of water so much that eventually you'll memorize it, but until that day arises, I will give it to you. Okay, so there's our beautiful equation. The density, remember, this one's all about the buoyant force, is all about the fluid. The force that the fluid is going to push with is how much mass gets displaced of the fluid. How do you figure out how much mass got displaced from a fluid? You take the density of the fluid and you multiply it by the volume of fluid displaced. How much volume of fluid was displaced? The mattress displaced all that fluid. So, long story short, the density of water is 1,000. That's going to be multiplied by how much fluid got displaced, which is the size of the mattress. And that's going to equal the mass of the person plus 2. 1,000 times 0.3 is going to be 300. Equals mass of person plus 2. So the mass of the person that could be held up is 298 kilograms. And this is all real numbers. Like a mattress that's 1 meter by 2 meters. So this is like a twin size. I don't know. A twin maybe? I don't know. It's like one of those single mattresses kind of things. This is all very reasonable numbers. And this is literally all you have to do to calculate how much a mattress can displace. Now, there is some slight caveats here. Depending on how you're standing here, the mattress will bend and stuff like that. So you might still get a little wet. But it will float. And 298 kilograms. Yeah, that's, remember 1 kilogram on Earth ends up being 2.2 pounds. Yeah, so if y'all had a mattress like this, it could float someone that's about 600 pounds. And so also, fun fact for you all, the Titanic. You know, if you watch the movie, everyone hates the whole, they could have fit another person on the door. You could actually calculate the buoyant force of a door based on how much fluid it would displace. The mass of the door, so you just find the mass of the door, you'd find how much fluid it displaced, and you could do the exact same it's literally this exact same calculation, and you could figure out how much mass a door could handle. Before it ended up underwater with just literally, it is this exact equation. It's this exact same problem, except the volume here would be the volume of a door, and you would have the mass of the door. Otherwise, you could do the math here and determine how much mass a door could. So just go measure a door, and you could do this problem, and the mass of a door. And you can figure it out. I think they did the math and said it couldn't. Oh. Nice. Okay. Well, but movie magic, you know, and all that.
It's all about the buoyancy.
Yeah, and it's so you all can do it yourself if you're like, would it work? You know, in the movie, they do lots of things in movies that make people not trust things, movie magic and all that. It does depend upon how dense the door is. So depending on what door is made of, steel versus, well, steel's not going to float. But whatever. I just know that's always one of the things. This is that problem. It's the exact same problem. So there you go. Fun, right? Floating. Okay. So I mentioned this. This is really what you all need to know, that the fraction submerged is just the density of the object over the density of fluid. It just comes from doing this, plugging in this values. The fraction submerged is literally defined as the volume of the fluid divided by the volume of the object that's kind of submerged. So it's really, really easy. So the density, the fraction submerged, equals density of the object over density of the fluid. An object has a density of 800 kilogram per meter cubed. What fraction of it will be above the water? Notice that I underlined the word above. Be careful. And it's a fraction. That's why there's no units. And then we're going to do 2 slides after this, and we'll call it good after that. 2 more slides, and then we're good. Yeah. This means there won't be that much left for Thursday, but we'll be able to have time. We do not have a fluids lab because I was like, 1, I haven't thought about one, and 2, I was like, man, if we have fluids in here, how do I prevent fluids from getting in here? No, there's no fluids lab. Not that I've thought about yet. The lab will be center of mass. Yeah. It's going to be a little mathy, but it'll be a cool lab. You all are going to find the mass of these meter sticks without using a scale.
No, because 0.80 submerged, the fraction submerged is equal to the pressure of the object over P fluid. So I got 0.80 from that calculation. That means 0.80 is submerged, which means that there's 0.20 of water.
For some reason, I got you.
All right, 10 more seconds. You all can totally do this math in your head. You can use a calculator if you want, though. Which I did learn, fun fact, the MCAT, you can't use a calculator, which I think is stupid. But.
You can use the calculator on the MCAT?
And also you have to have all the formulas memorized. It just sounds terrible. All right. 5, 4, 3, 2, 1. Good job. All right. Fraction submerged. Again, it's so easy. Like fraction, I have to kind of write the word every time. It stinks. There's no way to write shorthand of fraction submerged. Whatever. I'm going to write the whole thing again, which is a pain. What's the density of my object? 800 kilogram per meter cubed. What's the density of water? 1,000 kilogram per meter cubed. So how much is submerged? 4/5. Great. I didn't ask how much is submerged. I asked how much is above water. The rest of it. Yes, the answer is B. So fraction above water, fraction above equals 1 minus 4/5. Great. This is true of any object. So this is another way you all can find the density of any object out there. You literally just stick that object in water and see how much volume of it is above the or you just figure out the fraction of the fraction of the volume that's above the water, and you multiply it by 1,000, and so now you have the density of the object. Now that does get a little tricky if the object is a funky shape like a human being. You can't just say, oh, their head is above water and like do the height. It's the fraction of the volume. And so if you have a weird shaped object, this gets a little, like, you can't just look at it and tell. You got to do math. All right, great. All right, this next slide, again, I think this is pretty cool. This is a vocab thing. Apparent mass. How to phrase this? Well, here, this is the best way. Apparent mass is the mass of an object minus the mass of the fluid displaced. So this picture shows the apparent mass. Great, you got some object. It's out of water. It has a mass of 50 grams. How exciting. But then when I put it in water, so if this side's 50 grams, this side's 50 grams, right? Awesome. When you put it in water, it's not going to have this same apparent mass anymore. When you all go in water, is it really hard to jump? Yeah. You're like underwater. You can like float around. It's like you're in space and all that stuff. So in this example, this random example here, when you put something in water, you don't end up needing as much mass to kind of like lift it. So this is that apparent mass. This thing still has a mass of 50 grams, but you only need like 20 grams to kind of like lift it in the water. You all can pick up heavy stuff in water because there's a buoyant force helping you out. So, long story short, this apparent mass is so this 50 gram mass, when it's in water, it's like it's only 20 grams. If that makes sense. That's like, it's easier to lift up. They call it apparent mass because the forces help you out and whatever. And just to this, the apparent mass, it's because the buoyant force is helping you. What's the buoyant force? Mass of the fluid times G. So anywho, you can use this to find the density of an object. It's used to find the body fat percentage. I kind of mentioned to y'all. I don't know. They use lots of ways to find body fat percentage, but one of the ways is like they put you in a suit and then they submerge you in water and they measure the mass of you. And if they measure the mass of you when you're fully submerged, they can use it to figure out density and all that jazz. So here it is. Let's do it. This will be the last one we do. Let's find the density of a person. In an immersion measurement of a woman's density, she's found to have a mass of 62 kilograms in air and an apparent mass of 0.085 kilograms when completely submerged with lungs empty. It's very important that the lungs are empty because if you breathe in air, you all know this, when you breathe in air, you float better. Why? You are literally decreasing your average density because you're filling your body with air and the average density ends up being lower when you do so. All right, so what mass of water does she displace? This one kind of helps, it walks you through the problem. What mass of water does she displace? What's her volume? Calculate her density. And then we repeat it and says if her lung capacity is 1.7 liters, is she able to float without treading water with her lungs filled with air? I think I have to give you the density of air to do that, though.
Alright, so she displaces 0.0.
Which I don't know off the top of my head.
Minus 62 and then bring over
So apparent mass is nice and simple. You just subtract the two. Mass apparent equals the mass of the object, in this case the person, minus the mass of the fluid. Why do they quote unquote weigh less in water? Because the fluid is literally pushing them up. How much does the fluid push them up? The mass of the fluid times G, and G's all cancel out and all that good stuff. Yeah, so if there's 62 kilograms in air, but they're only 0.085 kilograms when in water, the difference between these is the mass of the fluid. That's how much the fluid is kind of helping out here. So, just 62 minus 0.085.
I just took 1,000, which is the density of water, and I tried counting it by 1/62, which is kilograms. I did, which is why I'm confused. Hi. So, volume, right? It's just I do 1,000 times 1/62.
All right, and then if you're figuring out the volume,
Cancel it because you can't just times it.
her volume is the exact same volume as the fluid.
No, cancel the 62.
They're the same thing. The volume of if they're fully in water, their volume is the exact same amount of volume of the water they're displacing. They're the exact same amount.
Yeah.
So if y'all can find the volume of the water, you know the volume of the person.
Numbers look right, but
This is how volume's often measured. If you want to measure the volume of something, you just stick it in water and see how much the water goes up.
So for her volume, you have density of water equals mass of water.
it's the mass of the water.
So because you
Oh, is it the mass of the water she displaced?
yes.
Okay, thank you. Okay, so I need to reframe my thinking. So, mass water, and then that should, so 1,000. No, I didn't get that.
So you are missing the externality.
Okay, cool.
So whenever mass and volume is mentioned, what equation are we going to use? Anytime mass and volume are ever mentioned, there's an equation that should come to mind.
1,000 divided by
Density equals mass over volume. Here's the problem though. If you want to find the volume of the person, you need to know the density of the person. Do we know the density of the person? We don't. We don't know the density of the person yet. So that's why we had to recognize the volume of the fluid is the volume of the person. If so here's some water. Yay! This water, let's say I have 20 milliliters. And then I put an object in it. A ball in it. And the volume is now 30 milliliters. What's the volume of my object? It's 10 milliliters. It's literally the amount the water went up. The same thing is true here. However much the volume of the water, they're the same. The amount of volume that's displaced is the volume of the person. So we're going to do this. So the density of the fluid equals the mass of the fluid times the volume of the fluid. So the volume of the fluid is going to equal the mass of the fluid divided by the density of the fluid. 61.915 divided by the density of water, which is 1,000.
And then you divide by this? Okay.
And you get the volume is 0.0619. And that is the volume of the person. They're the same. The volume of the water displaced is the same as the volume of the object because they're it's how much space the object takes up. All right, now you can find the person's density. You know the volume of the person. You know the mass of the person. And then part D, I have to give you the volume. I have to give you the density of air. Part D is like the first problem we did today. The gas can in the water. But I got to Google the density of water real quick. Sorry, density of air. Density of air.
I'm still working in B, sorry. So we're trying to find fluid. So what are we trying to find? We're trying to find
So yeah, density of the person is 62 divided by the volume.
treading water is like we're like floating on surface.
1001.62. Are they going to sink or float? Am I above 1,000 or below 1,000? I believe in you all. What say you all? Will this person sink or float? Sink. That's pretty important if you want to fully submerge them in water. That's why when they do this measurement, you got to get all the air out of your lungs. When you all do part D, your density changes. This is if you all have ever tried to float on your back. When you don't have air in your lungs, your body does start to sink. And you can test this for yourself. If you all ever want to sink in a pool, just breathe all the air out of your body, and you will sink. If you breathe in air, you will float because you are literally changing the overall density of your whole body, the average density, which is kind of cool.
So anything with a positive apparent mass is the same.
Yeah.
Yeah, I'm stuck on D.
So D is going to be like the first problem we did in class today. Where, yeah, you all have the mass of the person, and then, yeah, so you're going to get the total mass of everything and the total volume of everything.
Oh.
At least that's my current running theory. The air is not really going to change much when it comes to your mass. But it's going to increase the volume of your body. When you all breathe in, you're literally expanding the volume inside your body. Your lungs literally fill up with air and expand. You're increasing the volume of your entire body by just a little bit.
Is it mass of the person plus mass of the
Air.
Of the air? Mass of the air?
It's going to be like negligible.
Oh,
Because technically it's going to be a buoyant force from the air, right?
Yeah, so here if we just want density though.
So volume,
Oop.
volume of the air, yeah, volume of the person.
I think because of the buoyant force from the atmosphere, you could treat the air as massless.
Yeah, I mean so
62
Probably not quite that simple in real life.
yeah, so part D is literally the same problem that we did at the beginning of class. What's the overall density if there's air in the lungs? You're going to do the mass of the person plus the mass of air over the volume of the person plus the volume of the air. Before, when they breathed out everything, these terms were zero. Now they're not zero. You just got to find them, plug them in.
And massive air is negligible, you said?
Yeah, the density of air
Oh, density of air.
is going to be 1.225 kilograms per meter cubed. So when you do this math, the mass of the air is going to be negligible, but the volume is not negligible. The volume of the air in this problem is 1.75 liters, which is going to be 0.00175.
Density is mass. Her volume of the air is 1.75.
One day I'll get this through.
So hold on.
Yeah, so honestly, you could probably neglect the mass of air. If you do the math, you'll find it's not going to change much of anything. But it's good for you to see why that is. But the volume matters a lot. And then that's it. If y'all got this answer, awesome. If not, stick around. Up to you.
It's not, I keep feeling 35. I don't think 35 is the answer.
So mass of the air, I'll just calculate it for funsies. Density of air times volume of air equals 1.225 times 0.00175. This is not going to be shocking at all, but the mass of the air that you breathe in is very low. 0.002 kilograms. So when you all actually start plugging in the numbers here, your average density is going to be 62 plus 0.002. Hopefully you can see that that's really not going to change much on the top. But on the bottom, the volume of the person before was 0.0619, and now we're going to add that 0.00175, and that is going to make a big enough difference. But it is kind of cool that this problem is literally the first problem we did in class today in a new context. And yeah, it doesn't seem like that much, but it's enough. It's enough to make you float. And this makes sense. Your body is mostly water. Your body's density is really, really close to the density. Your original density when there's no air in it was 1001.62. That makes sense. Your body is 70% water. Your density is probably bigger than this value, honestly, but you have air dissolved in your bloodstream and all sorts of things and whatever. But yeah, just breathing in air lowers your density below that of water. So yeah, if you all have air in your lungs and this person, 97.4% of them would be submerged in water. Not that much would stick out of water, whatever, which is why you all have to tread water and all that jazz. Anywho. Yay, fluids! It's good. That's it for today, y'all.